Okay, thank you, Sabina, for the introduction, and thanks to the organizers for inviting me here. So for me, this is a little bit like a flashback through 20 years of working in non-volatile memories, meeting a lot of people I haven't spoken for many years, and up to what I'm doing recently. And this is similar for the topic I'm talking about, ferroelectric memories. So I would like to start with explaining why are ferroelectrics so good for non-volatile memories. And the reason is basically, in a ferroelectric, because of the crystal structure, you have two stable situations, two stable polarization states that are separated by a barrier, which is good to make it non-volatile. And at the same time, the switching between these two states can be strictly by an electrical field. So we don't have the inefficiencies that we normally have with all the other emerging memories in the switching process. And that's why ferroelectrics have been studied for a long time for non-volatile memories. So it all started back in the 50s, where people tried to do barium titanate with electrodes on it, and it failed because of disturbed issues. Then later on, in the late 80s, Ramtron came up, and they integrated the whole thing into a semiconductor process, used a similar approach like in DRAM, by adding a select transistor. They solved the issue, and since 1993, you can buy ferroelectric memories on the market. So it's actually not emerging, it's almost 25 years in commercial production. Nevertheless, it's failing to scale down as fast as other memories. And the reason is simply because the materials that you use here are very, very complicated. They are normally perovskites, or in some cases even layered perovskites, and you need on the one side a high thermal budget to even bring them into the crystal structure you need. And once you have this crystal structure, it's very sensitive to things like hydrogen or other attacks. So you have to do a lot of, I don't want to go into details here, a lot of things in the process to achieve a result, as you can see it in the devices that you can buy from Texas Instruments today. Moreover, since you are really sensing, I go back 2 slides, since you are really sensing actually the charge that is coming out during switching, during scaling, you have to maintain this charge, and you would have to go to the 3rd dimension, like in DRAM, to maintain enough charge if you go below 100 nanometers. And this is actually virtually impossible with PCT or SPT, because on the sidewalls of such a trench or stacked structures, you typically get the pyrochlore phase, and this is non-ferroelectric. So why do I still talk about ferroelectric memories? I could stop now and say it's very good for niche applications, but it will not go anywhere. The reason is, in 2007, a PhD student at Qimonda did some experiments to try to increase the K value of hafnium oxide. And he did something that was very popular at that time. He put different dopants in there to stabilize higher K phases. And for instance, he worked with silicon. And what he observed, in certain concentrations of silicon that he added, he all of a sudden got peaks in the CV curves. And they went to very high capacitance values. So he was interested in that because he was trying to increase the K value for the DRAMs. And he looked closer, and he found, when he measured polarization, that he got very nice hysteresis loops. And for some other concentration of the dopants, he got some antiferroelectric hysteresis loops. So this work went on, and in the last couple of years, we looked at different dopants, different ways of stabilizing this effect. And actually, you can do it with lots of different dopants. Aluminum, gadolinium, lanthanum, strontium. You can even do it with mixtures of zirconium and hafnium, which has become very popular because this is the easiest way to do it with a very wide process window. But what you can see from these data, this is data from ALD processes, this is data from PVD processes. The whole effect is very consistent. Even if not all the details are understood yet, we know today how to tailor the effect of ferroelectricity in hafnium oxide. Now the question is, why at all is hafnium oxide ferroelectric? This all came to us as a surprise to us. It is well known that there is an orthorhombic, non-centrosymmetric phase in hafnium oxide, but normally you only get that under extreme conditions of very high pressure. And it turns out that normally you get a monoclinic phase in hafnium oxide if you do annealing. You can stabilize higher symmetry phases like tetragonal or cubic phases if you add dopants. And it turns out that exactly at the boundary between these two phases, you seem to be able to stabilize the ferroelectric orthorhombic phase. Yeah, and you can do that with all kinds of different dopants. And for many years, it was a little bit speculative because with XRD data, you cannot really discriminate between phase mixtures of all three phases and only mixtures of monoclinic and tetragonal phases. But people from NC State just 2 years ago did some very nice work on position average convergent beam electron diffraction, and they could really show that the crystals that we get are non-centrosymmetric and that they only match to the PCA two-phase from the orthorhombic phase. Now, let's look at the parameters, and I want to bring two key points across from this table. If we compare the doped hafnium oxide with PCT or SPT or even PVD FTRFE, we will see immediately that the coercive field is much higher. The polarization is in a similar ballpark and not given in the table but stated here, the permittivity is much, much lower. We normally are used to call hafnium oxide a high K material, but actually it's a low K ferroelectric, and that'll be very important in what I will show you later on. But first of all, let's look at the first question is now answered. We can stable some sort of ferroelectricity in hafnium oxide. The second question is it useful for memories? So what we did, we looked at the switching characteristics, and you can clearly show you can make it faster with higher voltages. This is very consistent, and typically it can switch down to nanosecond speed, so that's pretty good, and we can really do reasonable programming of the device. Then we checked reliability, and in ferroelectric you have to be with retention a little bit careful because there is the so-called imprint effect. A ferroelectric tends to stabilize the polarization state it's stored in. Now, if after retention, if you reprogram the cell, then all of a sudden the other state will be unstable. So you have to measure also the retention of the other state. That's why you see so many curves here. But this is, it turns out that if you optimize the material, you get stable polarization in all states. And cycling is going up to 10 to the 9, 10 to the 10 cycles. And now there's a drawback of the high coercive field because typically cycling ends by hard breakdown because you're cycling pretty close to the breakdown field of the device. So this is one of the limitations. The cycling is very comparable to what you see in other ferroelectrics. First you see a wake up, then you see a stable phase, and then you see a fatigue. And we did extensive modeling and trying to understand what's happening. And it seems like in the wake-up phase, mainly the existing defects, which could be oxygen vacancies, but it could also be something else, are redistributed in the film. And then during the fatigue, we are generating new defects in the film. Yeah? So this can also help us to extend the cycling lifetime. I want to skip this one. This is just a comparison with PCT, showing that it does not drastically behave differently. If we want to integrate that into a memory, a very nice work that our colleagues from Fraunhofer CNT did, they integrated it into a vehicle with three-dimensional capacitors. And you can see here that you actually gain the effect of the increased area, something that could never have been demonstrated with PCT or SPT. So you can see from about 10 years ago, a lot of literature from Samsung and other people that tried that, but the material on the sidewalls was never ferroelectric. With hafnium oxide, it's easy to do that, and it works immediately. But having this in mind, having the cycling in mind and limited by breakdown, we are looking into ways how to increase the endurance. And if we look at this anti-ferroelectric behavior that we can get for some doping concentrations, then this turns out that this can cycle much longer. Unfortunately, it's not a non-volatile memory because it has no remnant polarization. So the idea is, let's try to shift the x-axis here to use only one of these halves, and then we have a non-volatile memory again. And we did that by changing the electrodes, by changing one of the electrodes to a high work function electrode. And indeed, then we can shift the polarization curve, and we only have one polarization that looks like a ferroelectric again. And with this trick, immediately we get much better cycling, which we have now pushed already to 10 to the 12 and beyond cycles in this type of concept. And it's also stable with respect to retention. Now, another way of doing a non-volatile memory out of the ferroelectric is to integrate it into a transistor. I have met few people here already that have worked with me previously on charge trapping devices, and we all know if we put a charge trapping layer into a transistor, we can use it as a non-volatile memory. And typically, if we apply a positive voltage, we get a positive VT shift, and the other way around if we apply a negative voltage. If we use the ferroelectric instead of a charge trapping layer, it will behave exactly the other way around. Positive voltage will end up in a negative VT shift. And what's important here is the memory window is not defined by the polarization. If anybody is interested, I can explain afterwards, because some people seem to be surprised by that. The memory window is defined by the coercive field multiplied by the thickness of the film. And I skipped this one because of lack of time. Another thing that is very important, it is of course a very natural idea of integrating the ferroelectric in a transistor. So why haven't we seen that? People have tried for decades to realize that. But if you put the ferroelectric in series with another dielectric that you need to have a stable interface to silicon, you will have a depolarization field which kills your retention. So there's this famous paper from T.B. Ma telling you why ferroelectric field effect transistors are still elusive. Now, if you try to fix that issue, you can increase the thickness of the ferroelectric, because then the capacitance of the ferroelectric will go down. So you can do such a device, which has been shown. So about 10 years ago, for the first time with SBT, non-volatile retention was shown. But obvious, this is not scalable. But if you use hafnium oxide, immediately you can do the same thing with a much thinner stack for two reasons. Coercive field is higher. Second thing, dielectric constant is lower. Yeah? And this slide shows that it really scales very nice. So it compares ferroelectric field effect transistors that we fabricated together with Global Foundries with 260 nanometer channel length and 32 nanometer channel length. And you see that the programming curves are more or less identical. And also retention is good. And cycling is more limited than in the capacitor case, because charge trapping is happening, as I showed you from the model. And in the transistor case, you are sensitive to the charge trapping. The transistor will react. So the window will close after about 10 to the 5, 10 to the 6 cycles. Currently, we think we can drastically improve it, but this is the actual status. And we went one step further. Together with Global Foundries, we integrated it into their 28 nanometer technology. And the first thing we were interested in is what will happen to the normal NFET and PFETs that we still need for the normal logic devices. And you can see here they are totally unchanged. So the, adding another device, the FEFET, does not change the CMOS. And also the FEFET works quite good for a first approach. So you can write something into the memory. You get some window between all the cells. It's still quite narrow, but it's there. And it behaves quite well after retention and also after cycling. So it's demonstrated that the material is not just in theory, but also practical, very easily to integrate in a modern CMOS process. When we did that, we found a very interesting side result. Once you have these small transistors that were never possible with other materials, all of a sudden you see steps in the programming curves. And we attribute this to switching of single domains. It's not fully proven yet that these are single domains, but it's very likely that this is. So you can also use this type of devices to study the ferroelectrics more deeply. And even these steps are very, very stable with respect to endurance and retention. I don't know, do I have a few more minutes or am I over my time already? Because I would like to skip the summary, but I would like to use the opportunity to also do a short outlook to two other applications of the material. And at least the first one, we get at least as much interest currently as we get for the memories. And this is the so-called negative capacitance field effect transistor. So many people talk about the so-called Boltzmann tyranny. That means that the subthreshold swing of the transistor is limited to 60 millivolts per decade. And if you go into the equation, you see that typically the depletion layer only makes it worse. You can never get better. Now assume then instead of just having this depletion layer, you have another series capacitance which is negative, then immediately you will get to better values. And because what's actually happening is you're amplifying the voltage at this internal node here, you even get much higher current out of the device. So it's not like in the tunnel FET where you get a better slope, but the on current is very limited. Here you even, if the concept would work, if you can solve this issue of the negative capacitance, you would even get more current out of the device. Now let's go back to a ferroelectric. Landau theory predicts this curve of the energy landscape via polarization or charge via energy. And you can see a normal if I look at a normal capacitor, and this is the voltage and this is the charge, then actually I would have one stable point at 0 volts and nothing else would happen. In the ferroelectric, I have these two minima, I have these two stable states, but in between I have a region that's locally going the other way around. So in principle, there I have my negative capacitance region, but of course, it's not stable. No? And the first thing we try to find out is, can we see it in our hafnium oxide? So what we did a measurement with a series resistance, and if there is a negative capacitance, we should see at some point in time that the voltage is not going up continuously like in a normal capacitor, but it should come down. And we really see that. So there is indication of negative capacitance. First step, because it's still transient, it's not stable, it's not useful for what I have shown, but I think it's an important result because you cannot be sure that you really have that in a multi-domain, multi-crystalline structure. Maybe in a single crystal, it's pretty obvious that you will see it, but the problem is the multi-domain structure. So now, what can we do about it? And you can look at literature on this topic. It is well established that theoretically you can put another capacitor in a series connection, and then if you get one intersection between the two curves, then the whole thing should be stable. So in this diagram, I would have a curve like this. So this would mean the series connection of the two capacitors will result in a higher capacitor than the one capacitor alone, which would be very useful for our transistor if we can do it. Now, we're not at the point yet. If you look into literature, you will find tons of papers that just use this equation, the Landau equation. Where did I have it? Oops, it's not on there, but the equation that describes this curve, the Landau equation, plug it into the device simulator and get tremendously good results. The problem about that is, if you do so, you assume the whole ferroelectric behaves like one domain, which is typically not what's going on in reality. So what we are currently concerned of is trying to find out, is it possible to stable these domains? And this is just a very preliminary result where we have made a very simple calculation. And in most demonstrations of negative capacitance field effect transistors, you will find that people put an internal metal electrode because they want to make the potential across the ferroelectric homogeneous. But if you do that, and if you do your energy landscape, you will see, if you assume now you have two ferroelectric domains, all of a sudden you get 4 stable states, of course, yeah? Because you not only have the ones where both point up or both point down, but you can also have the two in the opposite direction. And if you do the stability calculation, you find out that there's a saddle point here. So actually you cannot stabilize it that way. We conclude from this, better leave out this metal, but that's an interesting discussion that's going on because most papers that claim to have realized the device experimentally work with this internal metal electrode. Maybe there's still something else in there, I don't know. But it's a very exciting and interesting topic with a lot of scientific discussion going on. And finally, to conclude my slide, I want to give you a preview. Probably nobody will travel on to Kyoto, but on Thursday, we will also show that with the ferroelectric field effect transistor, you can do a spike time dependent plasticity, so you can also use that for neuromorphic computing. And we also see that the interest in this topic is rising. It's an alternative to some of the other approaches. But once you would have the device in a standard CMOS process, you could use it for a variety of things. So we're trying to add to this. And with this, I think I took a little too long. I thank you for the attention, and I'm open for questions, of course.